Alright, so we're going to do a little bit of review here of some radicals and rational exponents and radical equations. And you remember you can pause this video anytime that you would like to try a problem before I go through it. I'm not going to go through every single problem that is on the screen, but I will go through several problems and I'll try to make sure I tell you which one I'm about to do before I do it, so you can pause it if you would like to try it first. Many of these come from your homework, so you can go back and look and see how you did the first time and retry. So the first thing we're going to do is take a look at number 7, number 8, and number 9, 11, 12, and 13. 7, 8, and 9 ask you to rewrite the expression using rational exponents. So those expressions are radicals, and you're going to rewrite them into an exponent. So with number 7, you have the cube root of 12. So that is the exact same thing as 12 raised to the 1/3 power. Anytime you have a number raised to the first power and a root that is a cube root, it will be 1/3. The index is the bottom or denominator. The exponent of the number or variable on the inside is the numerator. Number 8, you have the 5th root of 8, so that would be 8 to the 1/5 power. Number 9, you have the square root of x to the 5th, so this would be x to the 5/2 power. Again, the 5 is the exponent in the numerator. The square root tells me that the denominator will be 2. So on the questions on your quiz that you have next class, you will be looking at changing radicals into exponents. You don't have to actually find the answer to these, so make sure you pay attention when it says rewrite. You're not actually finding the answer. Number 11, 12, and 13, you're basically doing the opposite thing. You are taking the exponent and you're rewriting into radical notation. So just go in reverse. 5 to the 1/4 power would be the 4th root of 5 to the first power. Now you don't have to write the little 1 for the first power, but again, the index comes from the bottom and the exponent on the inside comes from the top. Or the index is the denominator, the exponent on the inside is the numerator. And that works the same way that we did when we rewrote it to an exponent. It works the same way when we take an exponent to a radical. You're just working backwards or forwards. Number 12 is 7 to the 1/3 power. So you should have the cube root of 7. Notice, just like we had the cube root of 12 is 12 to the 1/3, 7 to the 1/3 is the cube root of 7. Number 13, you have 2t in parentheses. Notice it's in parentheses. Raised to the 1/3 power, that is the cube root of 2t to the first power. Now since that is 2t to the first power, you can also just do 2t without writing it as all to the first power, because 2 to the first power, t to the first power is what you have. Now if it was raised to the 2/3, you'd have to be a little careful because you'd have to square both of them or keep it in parentheses squared. The last one over here, I'm going to do number 14 also, just real quick as an extra here. X to the 7/6 or x to the 7/6 power would be the 6th root of x to the 7th power. Technically, you could also write it as the 6th root of x in parentheses to the 7th power, and that means the same thing. Most of the time, this is going to be the easiest, quickest way to write it. This is going to be more for if you got to do some work in your head versus in a calculator. Helps you do the root first and then raise to a power. So we're going to look at some of those similar to that here in just a little bit. The next thing is just evaluating expressions without using a calculator. Now, you will have the use of a calculator on the quiz, so you won't have to worry about evaluating without a calculator. But I just wanted to do a couple of these to make sure that you can understand what a root actually means. So if you saw one like number 22, and you were finding 8 to the 1/3 power, that is the same thing as the cube root of 8. We just talked about that on the other slide with the rewriting. Cube root of 8, 8 is a perfect cube. Remember, what a cube root is asking you is what times itself 3 times, or what to the 3rd power gives me 8. The answer to this would be 2, because 2 to the 3rd power is equal to 8. Or 2 times 2 times 2 is equal to 8. So whenever you're looking for a root, it's asking you whatever to that power gives me the number on the inside, or what times itself that many times. If you don't have some perfect cubes memorized, you are going to have to make sure that you use the calculator to do 2 cubed. If it's a 4th root, you're looking for whatever to the 4th power gives you that number. Take a look quickly at number 29. Number 29, you have the 4th root of 16 raised to the -7th power. We'll deal with that negative exponent in a second. Let's just go to the 4th root, since we were talking about possibly having a 4th root. So the 4th root of 16 is what times itself 4 times, or what to the 4th power gives me 16. That would also be 2. So you got to realize that 2 can be the cube root of 8, but it can also be the 4th root of 16. Don't get stuck in that whole perfect squares thing either. 16 is a perfect square, but we are looking at what to the 4th power. 2 to the 4th power is 16. Or what times itself 4 times. 2 times 2 times 2 times 2 is 16. So when you are asking a root, look at that index to figure out what power you're talking about. That lets you know what index, what kind of root you're looking at. So now let's talk about this negative exponent. It's been a little while since we've done some negative exponents, but remember, with a negative exponent, you always want to move it to the opposite part of the fraction and then make it positive. So this would be 1 over 2 to the 7th. Now, like I said on the quiz, you're going to have a calculator. You're not going to have to know what 2 to the 7th is, but it's just taking 2 times itself 7 times. So what you should end up with, if you multiply 2 times itself 7 times, or you do 2 to the 7th power, is 128. So this would be your answer, 1 over 128. So, I'm going to erase these now. We're going to do a couple more of these, just making sure we practice some roots here. Alright, so let's take a look at number 30. And I'm not just going in any particular order on these, I'm just kind of talking about some of the roots and things that we have done in this chapter. So 25 to the 3/2 power. Again, being able to rewrite this into a radical should be helpful. So if you'll remember back on the other page, one of the things I talked about is that this is a quick way to rewrite an exponent into a radical, but this way may help you more when you have situations where you may not have a calculator, or you're trying to evaluate and find the answer fairly quickly. So if you're looking in particular at this example that we're talking about right here on number 30, 25 to the 3/2 power, yes, is the same thing as the square root of 25 cubed. Remember, the 2 is the root, the 3 is the exponent. But it may be easier for you mathematically to do the square root of 25 cubed, which is the same thing. It's just the difference of multiplying them all together already, or doing the square root of 25 first and then cubing it. What is the square root of 25? It is 5. What is 5 cubed? It's 125. So this is a little bit easier to do, maybe if you're looking at something in your head, maybe. This right here, though, is still correct. This is just a little bit easier to do in your head. Now, if you're on the quiz, you can actually type this thing into the calculator exactly like it looks. So we're going to take a look at that here in just a second. Let's look at a calculator example. So on the calculator, let's take 25 to the 3/2 power. So if we take 25 and we raise it to the 3 divided by 2, that's how you would do 3/2, you will get 125, which is the same thing that we got when we just thought of it as a root. So when you are dealing with these on the quiz, I'm not going to have a calculator portion and a non-calculator portion, so you should be fine being able to type things like this in the calculator. So understanding how to do roots is still important, but you will have the aid of a calculator as well. So let's look at one more little example here, kind of an ugly example. Let's look at number 31. You have 64 to the negative 2/3 power. So let's deal with the negative exponent. That means I should move it down to the bottom of the fraction, because that's what we do with our negative exponents. We talked about that, sorry for going back to the wrong page. We talked about that previously with number 29 over here. But we are going to have 64 now raised to the 2/3 power. Still the 2/3 power, you just make the exponent positive when you move it down to the bottom. Now what is 64 to the 2/3 power? It's really the cube root, because the 3 on the bottom, of 64 squared. What is the cube root of 64? Remember, what times itself 3 times gives me 64? Or what to the 3rd power gives me 64? Again, what that means is when I go to my calculator, if I take 2 to the 3rd power, that is 8. 3 to the 3rd power, that is 27. 4 to the 3rd power, check it out, that is 64. So, what is the cube root of 64? That is 4. Because 4 to the 3rd power, or 4 times 4 times 4, is 64. So this is 1 over 4 squared, or 1 over 16. Now again, you could take this right here, and you could plug in 64 to the 2/3 power into your calculator as well, raising 64 to the 2 divided by 3, or 2/3 power, is 16. So this is going to be 16. Again, I know this said without a calculator, we are going to have no non-calculator portions on the quiz or the test. Alright, so the next section that we're going to look at here, you're going to have some evaluating that are just ugly roots, and I just want you to be able to take out your calculator and type them in. Just good calculator work. So we're going to take a look at number 35. And you have the 7th root of 1695. Now I know I joked in class about being able to teach my 4-year-old son how to do these roots. But seriously guys, it is important that you understand how to type these in the calculator. So this is the 7th root. We are getting a decimal approximation here. We are not trying to find an exact root. So we're going to take it our calculator. I'm going to type in 7. The reason is because I'm doing the 7th root, and underneath this menu, that is the math menu, I am going to go down to this root that says X root, or number 5. As soon as I hit that, the 7 automatically comes up into the radical, into the index. So then we're finding the 7th root of 1695. We press enter. we get 2.892743707, but round it to 2 decimal places, or 3 possibly sometimes, depending on how ugly the decimal places are. I'm just going to round that one to 2 decimal places. Same thing with one like number 37. You've got 85 to the 1/6 power. Yes, that really is the 6th root of 85, which you can type in that if you want to. But I hope you guys trust me. 85 raised to the 1/6 power is much quicker to type in even than the 6th root. That's the way I had to type them in when I was in school, because we didn't have this little root like you guys have for the 7th root or the 6th root. But it also is actually quicker. You get 2.0968. On this one, I would probably round this to 2.097. Probably go to 3 decimal places just because there's quite a few big numbers in a row right here. So 0.097 is what I would round it to. So on this section, you're just finding the decimal approximations. This is the one that everybody's going to love, the nice freebies, where you just plug it in the calculator. Just be careful with ones like number 40. Make sure that when you look at that, you got the 4th root of 187 to the 3rd power. Yes, you could try to do the 4th root in parentheses and then raise it to the 3rd power on the calculator, but it may be easier to do 187 to the 3/4 power. The 4 being the index goes on the bottom, the denominator. The 3 being the exponent goes on the top, the numerator. So this is actually easier to type in the calculator. So again, guys, when you go to find your answers on these, just go through and use the calculator, get the decimal approximation, and then round it to 2 or 3 decimal places. Again, on this one, probably go to 569, round it to 3 decimal places personally, just because that one's got several little big numbers there. Alright, so we're going to take a look just at a couple of equations here. Now this is not actually in the order that we did it in the chapter. This is kind of a little interjection here before we get into some simplifying with radicals. We're going to take a look at some of these basic equations. We actually did this last class when we were solving equations. So just a little bit on solving equations here. You have number 50, x cubed equals 125. Now notice it is x cubed, so the opposite of cubing something would be taking the cube root of something. And what you do to one side, you got to do to the other. So when you take the cube root of x cubed, think about what we did with variables inside a radical, or just think about, hey, it's the opposite. The cube root of x cubed would be just x. Then the cube root of 125, you can either use your calculator to help you find, or you can just remember that 125 is actually a perfect cube, 5 cubed. Or 5 times 5 times 5 is 125. So the answer would be 5. Notice that this is an odd root. Anytime we have an odd root, we talked about how you don't have to worry about putting a plus or minus, because negative 5 cubed would not be positive 125. So with these problems here, we're not going to spend a ton of time on these, but what you're doing is you're doing the opposite of raising something to a power. You're taking the root. So we'll do a couple more of these, but we'll look at number 52. X to the 6th plus 36 equals 100. First of all, if you subtract 36 on both sides, you get x to the 6th equals 64. Then, the opposite of raising something to the 6th power would be taking the 6th root. If you take the 6th root of x to the 6th, you get x. 6th root of 64, remember that's an even root, so we're going to put plus or minus. And then the 6th root of 64, if you use your calculator, or realize that it is a perfect sixth power. 2 to the sixth power is 64. So the answer would be positive or negative 2 because of that even root. That's why we put the plus or minus. That one's going to trip some of you up, but don't worry, I'm not going to put 9,000 of those on the quiz or the test. Let's take a look at number 53, and then we'll be done with this page. So x minus 5 to the fourth power equals 256. So if you have this parentheses to the fourth power, you can still take the fourth root. Now, up until this point, we would have had to do x minus 5, x minus 5, x minus 5, x minus 5, and multiply all that out with the FOIL method and the distributive property, then subtract the 256 over and get it equal to 0, and then, man, there'd be some factoring involved in that. That was from the Polynomials chapter. It'd be great fun. But now we have a way to find at least the real solutions, not the imaginary, by taking the fourth root because it's a perfect fourth power. So if you take the fourth root of x minus 5 to the fourth power, you get x minus 5. Again, you want to put plus or minus on the other side, just like you did with the sixth root, and then the fourth root of 256, you can either take your calculator out, or you can use your head. Since I've been talking about the calculator, I'm going to go ahead and show you what I mean. You can do a 4, hit the math button, go down to number 5 here, so it makes it a fourth root of 256, press enter, it's 4. 4 times 4 times 4 times 4, or 4 to the fourth power, is 256. But on this one, it is a little bit different because you still have the minus 5 over here with the x. You'll need to add the 5. Now, personally, I told you I like to put the positive 5 in front of the plus or minus symbol because I like that to remind myself about the plus or minus symbol. But it's also easier to type in the calculator when you get some uglier ones like we did in the past. Just don't forget to actually add. 5 plus 4 is 9. 5 minus 4 is 1. You do need to, from time to time, check these and make sure that you got the right answers. Also, watching out for when we get to some of the later ones with radicals in the equation, you got to watch out for extraneous solutions. Alright, so over the next couple of pages, we're going to be looking at simplifying with radicals and rational exponents. I am not going to go through every problem, and I'm going to hit some highlights. I told you guys in class, there is no way possible that I can actually hit every single possible question. I can just try to give you as many tools as possible, and then you have to know when to apply them. So I'll hit, like I said, a few highlights, but I'm not going through every problem, and I'm not going to be going extremely slow through these either. Remember, you can pause the video if you want to try them first. You can rewind the video if you need to see it again. Also, some of the add and subtracting and things like that you may do on the calculator, I'm probably going to do a majority of it in my head. So, let's take a look at number 3 first. Number 3, you have 5 to the 3/2 power times 5 to the 1/2 power. Whenever you multiply like bases, you add the exponents. So you leave the base the same, but you add 3/2 plus 1/2. Well, that's 3/2. That's 1/2. If you add 3/2 and 1/2, that is 4/2. 4/2, though, actually, if you use your calculator, will give you 2. So that's 5 squared, or 25. So your final answer for that one would be 25. But that's just using the property when you multiply like bases, you add the exponents. Take a look at number 4. You have 6 to the 2/3 power raised to the 1/2 power. When you have an exponent raised to another exponent, you multiply the exponents. Again, you don't do anything to the base. That's why they're called properties of exponents. So you raise an exponent to another exponent, you multiply. So what is 2/3 times 1/2? If you use your calculator, that is 1/3, because the 2's would end up canceling. Now, that also is equal to the cube root of 6. So I'm okay with either one of those answers. You could stop here because it is simplified even if you don't write it as a cube root. So, you may also run into some that have a negative exponent. Let's say like this one right here has the negative 1/3. So look at number 8. You have 7 to the 3rd, 4 to the 3rd, but it's the negative 1/3 on the outside. Now personally for me, I would raise both of these to the power on the outside first. Meaning, just like number 4 that I just did, when I multiply 3 times negative 1/3, that would actually be negative 1. 3 times negative 1/3 is negative 1. 4 to the 3rd, when you raise a power to a power, you multiply. So 3 times negative 1, don't change the base. 3 times negative 1/3 would be negative 1 again. What do you do with negative exponents? You move the 4 on the bottom to the top and make it positive 1. You move the 7 on the top to the bottom and make it positive 1. You move it and you make it positive. Now that is really just 4 over 7 because 4 to the 1st and 7 to the 1st. So, just a few examples there of using properties of exponents even when they are fractions. So let me see if I can get this to trash down here. So let's take a look at, how about number 10 here? You have 12 to the 3/5 power times 8 to the 3/5 power raised to the 5th power. Now these are not like bases, so don't do anything with the exponents on the inside. But you have a 5 on the outside, raising both of them to the 5th power. Watch what happens when you raise 3/5 to the 5th power. That's an exponent raised to an exponent, so you multiply 5 times 3/5, but don't change the base. 5 times 3/5, the 5's cancel, so it's 3. Same thing here. 3/5 is the exponent raised to another exponent. You multiply, so you get 8 to the 3rd. So you have 12 to the 3rd times 8 to the 3rd. Now you can take out your calculator and you can do that. 12 raised to the 3rd times 8 raised to the 3rd. Press enter. You get 884,736. Such a beautiful number. Now, some of you are going to say, well, Mr. Harrison, can I just type all that in right from the very beginning? Yeah, if you're really good at typing stuff on the calculator, you might could handle that. But simplifying it first makes this easier to type in the calculator. Technically, you could also do this. 12 times 8 to the 3rd is the same thing as 12 to the 3rd and 8 to the 3rd. And you could actually get the same answer. Alright, so on this page, we got a little bit of simplifying with radicals. Got some multiplying and dividing first. So let's take a look at number 15. Square root of 20 times the square root of 5. Remember, when you multiply radicals, they have to have the same index. These are both square roots. And then you just multiply the stuff on the inside. So what is 20 times 5? That is 100. What's the square root of 100? 10. Same thing with cube roots, like the cube root of 16 times the cube root of 4. They're both cube roots, so you can multiply them. So what is the cube root of 16 times the cube root of 4? That is the cube root of 16 times 4 is 64. What's the cube root of 64? 4. Again, you can use your calculator, or you can know that 4 to the third power is 64. So then you can also look at ones like number 18, where rewriting it may be beneficial. You've got the cube root of 3 and the fourth root of 3 raised to the 12th power. We can think of it like we did in the last problems on the last page. This is 12 to the 1/3. Sorry, that was an idiot mistake there. 3 to the 1/3. 3 to the 1/4, because I rewrote them as radicals from radicals to exponents. And then I'll raise it to the 12th power. 12 times 1/3 is 3 to the 4th. 12 times 1/3. 12 times 1/4 is 3 to the 3rd. So this will be 3 to the 7th. Because you multiply like bases, you add 4 and 3 together, you get 7. And 3 to the 7th, you would just use your calculator. 3 to the 7th is going to be pretty ugly here. So that is 2,187. Again, you're using your properties to simplify. So there's not always going to be one set way that you're always going to do it. You just use your properties to help you simplify with the radicals and with the exponents. Even on ones like number 20, you got the square root of 3, the square root of 75. You got to use the fact that you can take 75 and split it up into 25 times 3. Now, we haven't done one of those yet, but let's talk about that. 25 times 3 is 75. I don't think anybody would argue that that is not the case. The hard part is understanding, why did Mr. Harrison do that? Because 25 is a perfect square. This is a square root. How do I know it's a perfect square? I have them memorized. You may need the calculator to help you. But 25 divides into 75 3 times. What is the square root of 25? 5. And then this 3 stays on the inside. Now notice I have a square root of 3 on the top and the square root of 3 on the bottom. So this would actually cancel out to 1 over 5. Because this divides evenly into 1. Now that is not always going to happen. Sometimes you got to get the radical off the bottom of the fraction. So we may deal with one of those in a later period. Alright, so here's some simplifying in simplest form. Not taking out our calculator and just typing in the square root of 72. But taking 72 and splitting it up. Again, going through these quickly. You can pause, you can try on your own first, or you can rewind and watch again. 72 is 36 times 2. Why did I choose 36? Because 36 is a perfect square. This is a square root. 36 times 2 is 72. But what is the square root of 36? 6. What do I do with the 2? I leave it on the inside of the radical. This is simplified. Again, we're not trying to just type it in our calculator like we did earlier when it said evaluate. We are simplifying, okay? So, number 25. The 6th root of 256. We see if we can find a perfect 6th power that divides into 256. 2 to the 6th power is 64. 3 to the 6th power is 729. That's already too big of a number. So I just need to see if 256 is divisible by 64. Because 729 is already too big. And it is. 64 times 4 is 256. Because 256 divided by 64 is 4. Now again, why did I choose 64? because 2 to the 6th power is 64. And so that means the 6th root of 64 is 2, and the 4 stays on the inside. When I am dealing with things like number 29, you're not going to have a whole bunch of these that are extremely ugly like this. But the 4th root of 144, I want to see if I've got any perfect 4th powers that divide into 144 first. 2 to the 4th power is 16. 3 to the 4th power is 81. 4 to the 4th power is 256. That's already too big. So I take 144 and I divide it by 81. Now I hope most of us realize that's not going to divide. So then I try to divide it by 16. That was the other perfect 4th power, 2 to the 4th power. 9. 16 times 9 is 144. The reason we did that is because the 4th root of 16 is 2, and we leave the 9 on the inside. This is where these get kind of ugly though, because the 4th root of 9, the radical cannot stay on the bottom of the fraction. So we multiply it by the 4th root of something to make it a perfect 4th power. Again, it has to be a perfect 4th power so the radical will disappear. The 4th power that we want is 81. Why do I say 81? Because 3 to the 4th power is 81. I can multiply 9 by 9 and get 81. So on the top, 3 times the 4th root of 9 is 3 times the 4th root of 9. Or 3 on the 4th root of 9 is how we say that. On the bottom, the 2 stays on the bottom. The 4th root of 9 times the 4th root of 9 is the 4th root of 81, which is a perfect 4th power. It is the 4th root of 81 is 3. How do I know? Because 3 to the 4th power is 81. So 3 is the answer to this, times the 2 in the front is 6. So the only thing that you can do here is take this 3 over 6 and reduce it. 3 over 6 is 1/2. So the 4th root of 9 over 2. A lot of work for something that looks still pretty ugly. But again, remember we talked about the applications for this go beyond Algebra 2 into some things that are in your future, possibly depending on your major, depending on how many classes you take in high school or in college. So don't just ignore it just because you think you don't need it. We have some adding and subtracting with radicals as well. I'm not going to get into a bunch of these because if you got one like 32 and you're adding like radicals together, you have 2 6th roots of 3 plus 7 6th roots of 3. That is 9 6th roots of 3. Collect like terms is all that is. Well, Mr. Harrison, what if it looks like number 37 and they don't have like terms? What do I do? Well, you see if you can simplify this radical to get it to be a 7th root of 2. Now that's usually your clue to see if this will divide by 2 and see if it's a perfect 7th. But also you can start with 2 to the 7th power like we did on the previous page. That's 128. 3 to the 7th power is 2,187. Nope, too big. So 256, we want to see if it divides by 128. And it should. 256 divided by 128 is 2. So 128 times 2. Now again, why did we do that? Because the 7th root of 128, because 2 to the 7th power is 128, the 7th root of 128 is 2. Again, you could use your calculator if you need to, though. The 7th root of 128 is 2 times the 2 on the outside. That's 4. You leave the other 2 on the inside. So what is negative 6 on the 7th root of 2 plus 4 on the 7th root of 2? It's negative 2 on the 7th root of 2, because negative 6 plus 4. A little bit with variables and simplifying with expressions here. I'm not going to go through a lot of these, but if you run into something, let's say, like this guy here, number 49, we'll go with one that's kind of ugly here. You got the cube root of x squared times the 6th root of x to the 4th raised to the negative 3rd power. You can change these because they're not the same index. You can't multiply them. But you can change them to exponents of 2/3 and 4/6. Now, yes, I know 4/6 will reduce, but to keep things simple, I'm just going to look at this and say, hey, they're like bases now. I can add the exponents, 2/3 plus 4/6. So I can use my calculator if I need to do that, or I can go through and do it in my head. But 2/3 plus 4/6 is going to be 4/3. So this is x to the 4/3. If you multiply that, because this is an exponent raised to another exponent, when you have an exponent raised to another exponent, you multiply 4/3 times negative 3. You're going to end up with x to the negative 4th, which you then move to the bottom of the fraction and make it positive 4. So 1 over x to the 4th. Again, remember, you can pause, you can go back, you can rewind. I know I'm going through these fast, but these are all the same types of properties we've used numerous times on the other pages. You can go back and watch these again if you need to. Alright, so let's take a look at things that have variables and numbers, and we have to simplify within one radical, like 49x to the 5th. The square root of 49 is 7. Remember, the index on this one is understood to be a 2. So if you take it, remember what we did with a shortcut for variables was to say 2 goes into 5 twice with 1 left over. So you bring out x squared because it went into it twice, and you had 1 left over, so x to the 1st stays inside. 2 goes into 5 twice with 1 left over. You can do the same thing when you end up with one even as ugly as number 53, and you've got the 4th root of 12, x to the 2nd, y to the 6th, z to the 12th. I told you I'm not going to beat you over the head with these, but 4th root, remember 2 to the 4th power is 16, so the 4th root of 12 is going to stay inside. 4 does not go into 2, so it's x squared. 4 does go into 6 once, y to the 1st, with 2 left over, y squared. 4 does go into 12 3 times, so z to the 3rd, and none left over, so no z's left over on the inside. Again, the variables should be the easier ones when it comes to trying to see what comes out of the radical and what stays in. Alright, so the final thing that we're going to look at is how to solve equations with radicals in them. And basically, this is the same thing that we did earlier where we solved equations with high degrees of exponents. You just want to do the opposite operation. So if you look at one, like number 3, you are taking a square root of 5x plus 1 equals 6, the first thing you want to do is make sure the radical is isolated. But then you just do the opposite of the square root, which would be to square both sides. If you square the square root, it disappears. Don't do anything weird with the numbers on the inside. 6 squared is 36. Then you just subtract 1 from both sides. You get 35. Divide by 5 on both sides. And you get x is equal to 7. So when you are doing these, you just want to do the opposite operation. The opposite of square root is to square something. Just be careful if you run into ones like number 8, where you have 8 times the square root of 10x minus 7 equals 9, because you have several things that are not in the radical that you need to move out of the way first, instead of trying to square everything first. So, you take the 7 here, and you add 7 first, just like I would in a normal equation. It gives me 16. Then this 8 is in front, it is multiplying, so we divide by 8 on both sides. We get the square root of 10x equals 2. Now that you have the radical isolated, you can square both sides. Because it's a square root, we get rid of it by squaring both sides. 2 squared is 4, and then you divide by 10. You get x is equal to 0.4 as a decimal, or 2/5 as a fraction. So, when you have just a simple square root equation to solve, make sure you isolate the radical first. Then you want to square both sides if it's a square root. If it was a cube root, you want to go through the same concept. Like number 14, you have the cube root of x minus 16 equal to 2. The opposite of a cube root is to take both sides and cube it. The opposite of a cube root would be to cube both sides. What you do to one side, you got to do the other, right? Well, when you cube a cube root, it disappears as well. 2 cubed is 8. And then you add 16 to both sides. What is 8 plus 16? That's 24. Same thing if you saw something like number 21 here or like number 17 here. If you needed to move stuff away from the cube root first, you do the same thing like we did here on number 8, where we added the 7 first, then divided by the 8. Same concept here. You would subtract the 12, then divide by -5, then cube both sides. I'm not going to do a lot of those, but the opposite of a cube root is to cube both sides. Just like what we did earlier, the opposite of cubing something is to take the cube root. Alright? Then we had some that looked like these, where you had a rational exponent. So first of all, the first thought, like you should see normally, is divide by 2 to get the x by itself. But it's x to the 2/3 power. What's 32 divided by 2? That's 16. So you got x to the 2/3 power. Now x to the 2/3 power, what it really means is it really means the cube root of x squared equals 16. Because that's that exponent as a radical. But this would cause me to have to do 2 steps. I'd have to cube it to get rid of the cube root. Then I'd have to take the square root to get rid of the x squared. So instead of doing that, I showed you a way to get rid of the 2/3 by raising both sides actually to the 3/2 power. Why? because the 3/2 power is the same thing that you would do over here when you raise it to the 3rd power and you square root, because this is the 3rd power and the 2 on the bottom is the square root. So instead of doing 2 steps like you would here, you only have to do 1, because what happens to 2/3 times 3/2 when you raise a power to a power, you multiply, you get 1, because the 2's cancel, the 3's cancel. Then you have 16 to the 3/2 power. You can use your calculator to do 16 to the 3/2 power, or you can take it and you could even do the square root of 16, which is 4, to the 3rd power. It's 64. You can use your calculator, you can use your brain. Either way, it's 64. But there is something that'll throw you off on this one. It's a square root, a 2 on the bottom. So that does mean you have to remember to put your plus or minus, just like we did any other time we solved using an even numbered root. If it's an odd root, you don't have to do that. So if you look at one, let's say, like number 24, and you have 1/2 x to the 5/2 power equals 16, the first thing you could do is you can multiply both sides by 2, because that is going to get rid of the 1/2. 2 times 1/2 is 1, so that gets rid of the 1/2. 2 times 16 is 32. Notice I multiplied by 2. Now I'm going to raise both sides to the 2/5 power, just like I did earlier. To get rid of the 2/3, I raised it to the 3/2. To get rid of the 5/2, I raise it to the 2/5, because those will cancel out. And 32 to the 2/5 power, that's a 5th root, because the 5 on the bottom. That really means the 5th root of 32 squared. So that is the same thing as 2 to the 2nd power, or 4. If you use your calculator, 32 raised to the 2/5 power, sorry about the parentheses there, will give you 4, just like we got here. Notice that is an odd numbered root on the bottom, so 4 doesn't need the plus or minus like the even numbered roots. One thing that you can run into sometimes with these is also extraneous solutions. I'm only going to do one of these. You're going to take a look at number 34. You have x minus 6 equals the square root of 36. When you want to get rid of the square root, you have to square it, but you also have to do that on the other side, and that causes an issue on this problem. And I don't know why I did 36 right here. Well, let's fix that. That's 3x right here. So 3x, when I square the square root, what comes out is 3x. I apologize for that, messing that up. But on the other side, x minus 6 squared really means x minus 6 times x minus 6. Which means you're going to have to do x times x. That's x squared. X times negative 6 is negative 6x. Negative 6 times x again is another negative 6x. Negative 6 times negative 6 is positive 36. That is x squared, sorry guys, minus 12x plus 36 equal to 3x. This requires you to go back and be able to solve equations like we've done numerous times now with quadratic equations using the the factoring method, quadratic formula. You can sing the song on your own, or even completing the square sometimes. I would subtract the 3x over and get negative 15x, because if you subtract 3, it's negative 15. And I would try to see if I could factor it before I tried to go to the quadratic formula. So the factors are x and x there. Plus 36 here means I gotta have a negative and a negative because the middle is negative. I'm not going to do a review of factoring here. If you need to review factoring, go back and watch some of my older videos on how to factor, because many of you still need to work on that, and that's okay. You just need to go do it on your own. So what are the factors of 36? 1 times 36, 2 times 18, 3 times 12. 3 times 12, 3 and 12 would give me 15, wouldn't it? So sometimes you may have to go on and say, oh, then 4 times 9 or 6 times 6 is also 36. But remember, you're trying to get 15 out of that FOIL method, just like we saw earlier. If you multiply x times negative 12, negative 3 times x, and negative 3 times negative 12, you should get this. Some of you are forgetting where factoring comes from still. Now the final step is to set each factor equal to 0. These miniature equations that you get, because this times this equals nothing, that means one of them has to be nothing. You get x is equal to 3, and you get x is equal to 12. Two really quick equations. Now be careful on this one, because 12 does work when you plug in 12 into the original equation. 12 times 3 is 36. The square root is 36 is 6. 12 minus 6 is 6. It works. But if you look at this one with 3 plugged in, 3 times 3 is 9. The square root of 9 would be 3. But 3 minus 6 would be negative 3. That does not work. So, this is what we call an extraneous solution. An extraneous solution. Because it doesn't work in the original problem the way the original problem was written. The final thing I'm going to look at is what happens if you have more than one root in the same problem. And we're going to take a look at one that you could see, for instance, like number 45, where you have the square root of 4x plus 1 equal the square root of x plus 10. You have a square root on both sides, so you square one side to get rid of the square root. What you do to one side, you gotta do to the other, and you end up with a square root canceling out on both sides. And then your equation is back to just solving like you've done before in the first chapter of the year. You subtract x, that is 3x. You subtract 1, that is 9. And you divide by 3, that is x is equal to 3. And you could plug it in, and you'd see that you got the square root of 13 equals the square root of 13, which is true. If you saw one like number 46, you would need to move this radical over to the other side first. And it's a cube root, so you cube both sides. Now, I will warn you ahead of time, if you get into something like number 49 that are pretty ugly here, and you square both sides of this, you're going to have a lot to try to cancel out, and you're going to still end up with a radical on one side, on this side, even after you square it, and you're going to still have to square it again after you get that radical by itself. So it could get really ugly sometimes with these. Don't worry again, I'm not going to try to throw ridiculously ugly ones at you for no reason. So, that is a blitz review of everything we've done so far in this chapter with radicals, rational exponents, and radical equations. Again, go back and watch them again if you need to go back and watch them again. Pause and try beforehand. Mr. Harrison goes through them. If you don't like my video, go find another video. It doesn't bother me if you find somebody else that can teach you radicals. I want you to learn them. I would rather you listen to me in class, and I would rather you watch my videos and learn from somebody who's, closely connected with you. But it's okay if you learn them through somebody else. It's not going to hurt my feelings. So, hope you guys enjoyed this video and can use it to help you study for your quiz or just for your test. Either way.